Hi, I'm Matt and today I'm going to give a demonstration on our Toolbox IQM-Vis, which is used to visualize and evaluate image quality metrics. It's a Python package available to download via PyPy, as you can see here, and we have online documentation which shows how to use, install and customize the package. So we can see how to install it here. There's various tutorials on the different features of our package, which I'll get into later. We've also got the documentation as well. IQM-Vis is an open source project, so our source code is on GitHub as well, as you can see here. Okay, so let's start by taking a look at the interface of IQM-Vis. On the left, we have our test image, and we can scroll through different images in our dataset that we've chosen. And on the right, we have the distorted version of this image. This is just so we can see that the different distortions having the desired effect on the image. Whilst adjusting these distortions, we can also see on the right here how these affect the different image quality metrics and the scores that they give. There are more graphs to look at here as well on the right hand side, such as the radar plot, which shows the mean value for each metric over the whole parameter range of each distortion. This serves as a quick way of comparing sensitivities to specific distortions for each image quality metric that we wish to evaluate. We can also go into a bit more detail by looking at the range plots for each specific distortion. This is to get a bit more of a detailed picture on how each IQM responds for each proportion of the parameter range. So here we have brightness. We can see the contrast for each image quality metric and hue. We also have some correlation plots, which I'll get into later on. Okay, so now that we're familiar with the interface of IQM-Vis, let's take a quick evaluation of a recent image quality metric called DISTS, which I'll show you their GitHub here. DISTS is supposed to be invariant to small geometric changes in images, such as translations, small zoomings, and rotations. So let's uncover what this actually means for a specific image distribution. So for this, we'll use a textures dataset, which I've got preloaded here into another instance of IQM-Vis. And I've applied a crop to the images so that the geometric transformations don't induce edge artifacts. So as you can see here, rotation, we don't get any black edges, and neither for X shift. Okay, so as we can see from the radar plot, this seems to be much less sensitive to geometric transformations as NLPD and SSIM. But let's have a look at the range plots to get a bit more in-depth analysis. So on rotation here, we can see that DIST has a similar response to other deep learning methods such as LPIPs. So yeah, for rotation, similar to LPIPs, but not as sensitive as SSIM and NLPD. Similar story for X shift, a bit less sensitive than LPIPs. So as we can see, DIST is providing sort of a similar geometric insensitivity as LPIPs. Similar story for zoom. So from here we can make a more informed decision of how this new metric DISTS is comparing to other traditional ones such as LPIPs, NLPD and SSIM. Okay, now so we're going to go through the human perception experiment feature of IQM-Vis. We'll go back to our other interface. So this will come into our correlation plots that I was talking about earlier. So human perception scores are very important when assessing and designing image quality metrics, since humans often ultimately will be the end users of viewing image data. And today we'll just go through a simple experiment where the participant will choose an ordering of an image on different range of distortions. So for this, we'll get rid of the distortions we don't care about, since we just want to do a quick experiment. We'll do it for some noise here, salt and pepper noise. So this looks like this. And let's actually load a new set of images. So we'll just load the Kodak images up instead. So yeah, we'll do it for this image. Okay, so what's important for experiments is we want the image to be the correct display size. So calibrate the display, which is a bit bigger. And then also we can do the screen display brightness, which is 250 for my display, so that's perfect. Okay, so now we've got all of the things we need to set up for an experiment, which is the image, the distortion, and the settings. We can then go ahead and run the experiment. Okay, so running the experiment, we go into the full screen mode, and this is the first screen which the person setting up the experiment just can view that all the settings are correct here. And once we verify that everything's correct, we can click set up and pass over to the participant, where they're given a bit of information on the experiment, and they can click start. Okay, so the background goes black just so it doesn't interfere with the viewing of the image. And then we click the reference on the top, and we click the one which is less distorted, which is this one on the left, and then right. And we keep doing this recursively until the underlying sorting algorithm has come to a conclusion. So I'm just clicking through, clicking on each of the ones that I believe to be most similar to the reference one above. There we are. So from that two-step discrimination process, we have the experiment sorting order. So as we can see, actually does follow the parameter values up quite well. So we can quit this. And here we can see the correlation plots against the experiment we just did. So we can see it does correlate well against mean squared error, NLPD, and SSIM. But let's say one of these was a bit away from the correlation, and we wanted to investigate which exact image didn't break the correlation. So we can click on these, and it will show us here what that image actually is. Okay, so that wraps up this quick demo of IQM-Vis. I hope you found it useful, and I'll just refer you back to the documentation again. If you have any questions, feel free to look through here or email me, and I hope you find IQM-Vis helpful. Cheers.